Welcome everybody to Algebra 2, Section 6.7, Inverse Functions. So just like when we talked about actual functions, we had to talk about relations first. So when we're talking about inverse functions, we first have to start with inverse relations. And an inverse relation, well first, we take whatever our relation r is, and we write it as r as if it's to the power of -1. But we're not actually taking something to the power of -1 like where we reciprocate or move where it is in the fraction, but rather we're just notating, or this is how we write that this is the inverse of relation r. So we just say inverse relation. And so to find the inverse of relation, what you do is you switch the x and y values. And that's within individual ordered pairs, for example. And so what we are going to be looking for today is specifically is a one-to-one relationship. We're going to be analyzing whether or not functions and relations have a one-to-one relationship. Now, what that is a function has a one-to-one relationship if the relation and, very important that the word and there, its inverse. You write its to make it more look like one word. Are both functions. So it's considered one-to-one if both the original relation and the inverse relation are both functions. So let's take this relation r in example 1 here. Let's find the inverse relation and then establish whether the original is a function, the inverse is a function, and then thus is the relation one-to-one. So to find our inverse relation, we're just going to take individual ordered pairs and flip around the x and y. So -2, 1 flips around this x and y, for example. Then 4, 2, -1, 3. And I should be putting commas between these ordered pairs. And -2, 4. Now notice I didn't necessarily concern myself with the fact that they were least to greatest for x for the new x values, the old y values. Technically, should I, when I'm ordering relation? Yes, but for the purposes of just making the inverse relation, this is sufficient just to at least write them down. Now, is the original a function? Well, reminder, to verify whether or not something's a function, we have to establish that each x goes to exactly one y. So in our original function, we have 1, 2, 3, and 4. 4 different x's going to a y, each of their own. So they're each going to only one y, I should say. Not each of their own, but they're each going to one y. So is the original a function? Yes. Now is the inverse a function? Okay, so in this new one, we have to follow the same rule. We say, is each x going to only one y? And we say, no, actually. -2 has two y's. It's going to both 1 and 4. And so no, second one's not a function. And so is it one-to-one? No, it is not one-to-one, because the inverse is not a function, even though the original one is. Now, we could have known it's one-to-one without answering these individual questions, and it's actually, in a way, we could answer the individual questions on the way. And it's actually with only looking at this one and not even looking at the inverse. And that's by establishing, okay, do any of the x's repeat themselves? If the answer is yes, then the original is not a function. If the answer is no, then the original is a function. And then we ask the same question for y. But this time that impacts the inverse. And so do any of the y's repeat? If there are no y's that repeat, the inverse is a function. And if there are y's that repeat in the original, then the inverse is not a function. And because there were y's that repeated, when we made the inverse, they became x's that repeated or went to multiple y's, thus making the inverse not a function. So example 2, I can tell you right away that it will not be 1-to-1 because we have some x's repeating. So if either x's or y's repeat, it won't be 1-to-1, even though either the original or the inverse would still be a function potentially. So let's find the inverse though. That would be 5, 1, 6, 1, negative 4, 3, and 9, 4. So is the original a function? No, because those ones repeat. Is the inverse a function? Yes, no x's repeat. Is it 1-to-1? No. For the reasons we mentioned previously. Number 3 here, we have a mapping diagram being shown. So to find the inverse relation here, I'm just going to do ordered pairs since it gives me a line here to list. And so it's going to go from y value to x value with the y value of -5 just being there just because, I suppose, never actually used. And so we reverse the arrow. So it goes 2 to 1, 6 to 0, and 6 to 11. And is the original a function? Yes. None of the x values repeat. Is the inverse a function? No. The 6 repeats. And so is it 1-to-1? Also no. So all 3 examples we did were not 1-to-1. But once again, what it would look like for it to be 1-to-1 is if both the original and the inverse were functions, which would be the case if no x's and no y's repeated. Now, horizontal line test, that's new because we have a vertical line test. Recall the vertical line test. That's used to determine whether a relation is a function. And how that works is you draw vertical lines, and if the rule is that if any one vertical line were to ever hit more than one point on the graph, then it would be not a function, not be a function. And once again, if any vertical line hits more than one function, so not, less than one or exactly one is fine, but just if any vertical line were to hit more than one, that's an issue. Now, the horizontal line test is used to determine whether the inverse would also be a relation or not. And the horizontal line test tells us the same thing, but just with a horizontal line. And says if we draw a horizontal line across, would it intersect more than one time? So same rules as the vertical line, just now it's horizontally. Very similar to how we had up here, checking for x's and y's in our original relation. Allowed us to check for the original and the inverse at the same time. The vertical line test allows us to check the original relation here to see if it's a function. The horizontal line test allows us to check the inverse to see if it's going to be a relation or not without even seeing the inverse or finding the inverse or anything like that. And so we can see on number 4, for example, that yes, the inverse would be a function because it does pass a horizontal line test. No horizontal line would hit more than one point. And so yes, it is 1-to-1 because it passes both the vertical and horizontal line test because both the original and the inverse relations are functions. On number 5, it passes the vertical line test all day long, but it would fail the horizontal line test at many points. For example, right here, hitting the graph at more than one point, exactly 4 to be precise. And so no, this is not 1-to-1 because it does not pass the horizontal line test, and thus the inverse is not a function. And if either original or the inverse were not functions, then it will not be 1-to-1. Moving on to the next page. So now we're going to work on finding inverse functions, not just inverse relations, and identifying an inverse, whether an inverse is a function. So the inverse of a function, f of x, is written as f inverse of x. And so we write that -1 again, just like we did on the relation. And just like on the relation, doesn't mean we actually apply a negative exponent and use exponent rules such as moving it to the bottom of a fraction or anything. It just means that we are going to be putting it on the, I apologize, it just means that we're going to be calling it the inverse of that relation. So we say f inverse of x is how we pronounce that. So in order to find the inverse, what we're going to do is we're going to, first of all, just replace f of x with y. And some of us may end up skipping this step mentally, and that's fine. But remembering that f of x and y are the same thing. And then we're going to interchange or switch x with y just like we did a moment ago when finding the inverse of a relation. Then what we'll do is we'll solve for y, and then we're going to rewrite y as f inverse of x. So essentially the opposite of step 1. So step 1 is rewriting f of x as y, and step 4 is putting it back into function notation, but this time as the inverse rather than the original function itself. So step 6 here, or example 6 here, as we find the inverse of this function. So I'll make it y equals 5x. Replace y and x with each other, or swap them, and give me, I should emphasize my y there, and that would get me x equals 5y. Now I'm on to step 3 where my goal is to solve for y. So I'm going to divide both sides by 5, which I get 5 over x equals y. So now I'm going to replace y with f inverse of x, giving me f inverse of x equals 5 over x. And that would be my answer. I must apologize earlier. I wrote the -1 in the wrong spot. I need to go back and fix that. There we go. It's f inverse of x is how we read that again. So I apologize for how I wrote that earlier. Example 7 here. Y equals x minus 7. We just replace f of x with y. Once again, a lot of us may end up just skipping that step mentally, which is more than fine. If you find that you benefit from that step, then please, by all means, continue writing that step. Then we do step 2 where we change x and y with each other, or switch them, where we get x equals y minus 7. Then I solve for y, step 3, where I add 7 to both sides, and I get x plus 7 equals y. And then I replace y with f inverse of x. And I just notice I swapped my equation around again, just like writing the f inverse of x on the left, which is how we do function notation. So on number 8, a little bit more going on with x is being subtracted and divided. We'll see how that pans out here. So y equals x minus 8 over 3. We'll switch around x and y. Start by multiplying since the whole thing is being divided. So I'll get 3x equals y minus 8. Then I'll add 8, giving me 3x plus 8 equals y. So now I'm going to rewrite my answer as f inverse of x equals 3x plus 8. And that'd be my answer. So next up for number 9 here, replace f of x with y. And start solving for x. And then switch x and y around. And start solving for y. So I'll subtract 1 here. And then I'll multiply both sides by -5/2, the reciprocal. And I'll distribute that on the left side, so I'll get -5/2x plus 5/2 equals y. And so I'll have f inverse of x equals -5/2x plus 5/2. On number 10 here, note we have a restriction. We're told if x is greater than or equal to 0, that this would be true. And so let's see what we get when what happens when we don't worry about that right now, essentially. I'm not concerned about that restriction. I don't want you to be concerned about that restriction right now. We're just saying we don't want to plug any negative numbers in there. And that's purely for the purposes of what our pardon me, what our inverse will be. But we'll see our inverse in just a moment, and it'll actually have its own restriction, which I'm not going to have you guys worry about necessarily finding by any means either. So handle this the same way. Replace f of x with y, and then switch y and x. So we get x equals y squared minus 9, and then start solving for y. So I'll add 9 to both sides, and then I'll undo the square by square rooting the whole side. So the square root of x plus 9 equals y. And we were restricted to just positives, which is why we're not doing positive and negative, the plus minus there, although normally we would have plus minus there. That's where that comes into play. So that's why I wanted to just say, hey, don't worry about it for now. But it, that's when it comes up. Anyway, and so this would be f inverse of x equals the square root of x plus 9. And we're going to restrict this to when x is greater than or equal to negative 9. And the reason why is because that's what would make this radical at 0 or greater. Negative 9 would make it 0, and as long as it's greater than negative 9, it would be positive. If it were to dip below or less than negative 9, then we would have a radical of a negative number, thus giving us imaginary parts which are not parts of functions. Once again, I'm not going to have you worry about finding restrictions on your own, though. Number 11. So once again, swap around x, or switch f of x for y. And then swap x and y. I'll add 6 to both sides. And then we learned in unit 6, section 6, so just last section, that we would cube root both sides to undo the cube. So that would give me the cube root of x plus 6 equals y plus 4. And the reason you don't get positive negative here is because you don't have positive negative when you do an odd root. I had to keep getting y by itself, so I will subtract by 4. And so I would get the cube root of x plus 6 minus 4 equals y. So f inverse of x is equal to the cube root of x plus 6 minus 4. Now, let's just say you're given two functions, f of x and g of x, for example, and most commonly. How would you verify or test if they are inverses? Unless you wanted to go through the work of finding the inverse of one and to see if it's the inverse of the other, or to see if you get the other one, which is certainly one way to do it. You're able to verify it by composing. So f of g of x equals x. If you plug g of x into f of x, the second function into the first function, you'll end up just simplifying down to x. And it would work the other way around too. If you plug the first function into the second function, it would also just simplify down to x. They end up undoing each other because anything in its inverse undo each other. Addition and subtraction are inverses, they undo each other. Multiplication and division are inverses, they undo each other. Square and square rooting are inverses, they undo each other. So a function and its inverse, when composed, when plugging one into the other, they undo each other and you just get x. So in order to verify if two functions are inverses, you compose them each direction, you plug one into the other and then the other direction as well. And if you get just x after simplifying, after doing both directions, then yes, they are inverses. So on these examples, determine whether the pair of functions are inverse functions. So we'll plug one into the other. So note here, we're not doing like f of g of 2. We're plugging 2 into g and then that result into f like we were doing in Unit 5. Rather, when we do f of g of x, we're plugging this entire thing in where x goes. So instead of x being squared, it's the square root of x minus 8 being squared. And if it lets me write it, we might see what would happen here. But that might be a big if. And then we keep writing plus 8. So I took this and I plugged it into x just like if it was any number instead of being an expression. Now we know a square root and a square undo each other, so they undo each other. We just get x minus 8. And if we add 8 to that, we just get x. And so sure enough, f of g of x gave me x. And so, yep, that worked out. So I'll put a little check and say, yep, checked it. And so now I have to check the other direction too. G of f of x. If I do the square root of x squared plus 8 instead of x, I plugged in x squared plus 8, and then I subtract 8 from that, I should get x. And so as we plug this in and check, I get the square root of x squared. 8 minus 8 is 0. And I am just getting the square root and square undoing each other, and I get x. So again, as we compose, we just get x, and it checks out. So we determined that yes, they are in fact inverses, and we proved it algebraically. Algebraically means by doing the equations, or algebra. On number 13, let's try this here. So if I do f of g of x, and it doesn't matter which way you start, by the way, to be clear, whether you do f of g or g of f first. If I do negative 4 and I plug this into that, x over 4 minus 5, and then I add 5 to this. As I distribute my negative 4, I get negative 1x, as these negative 4s, or these 4s reduce, plus 20 plus 5, and I can tell, oh, that won't do what I want it to do at all, actually. That's a negative x plus 25, not just x. And so f of g of x did not equal x, and so thus these are not inverses. I didn't even need to bother checking the other direction, g of f of x, and whether or not it had worked doesn't matter. If g of f of x worked, cool. If it doesn't work, cool. Either way, these are not inverses. Oh, I didn't box my original answer on, or my answer on number 12. But anyway, the reason these aren't inverses on number 13 is because it doesn't work both directions. So as soon as you realize it won't work one direction, that is enough. On to our last page for this unit, graphing inverse functions. And so what we're going to do here is we're going to graph a triangle. We're given triangle ABC by these points, negative 1, 6, and so on and so forth. And so first, we're actually told to write the inverse. And so the inverse of the relation, I'll just flip around the points, 6, negative 1, 2, negative 7, and negative 3, negative 5. Then we're told to graph the original and its inverse. So I'll graph the original in green and the inverse in red. So they pop. So negative 1, 6, negative 7, 2, and negative 5, negative 3. And then I'll graph the new. Oh, that was 6, positive 1. There we go. Oh, what did I do wrong there? Oh, -3 comma -5. I plotted that one wrong. There we go. I went +3 and I expected this to work. Which, spoiler alert, it didn't. There we go. We notice that these kind of looks like the same triangle, just moved. Oh, okay. What do we notice about the graph? Well, I'm kind of talking about that here. Well, what happens is if we draw this dashed line y equals x is just a dashed line going through all of these middle points. It starts at the origin and goes up 1 over 1 with the slope of 1, or down 1, left 1 with the slope of 1. It reflects it perfectly. It reflects it perfectly across those. So, for example, if we were to measure the distance here, perfect distance across, and perfect distance across at all 3 points away from that line. And so it reflects across y equals x. And that's true for any inverse functions. When you graph them, they will always reflect across y equals x. And so what we're going to do here on 14, 15, and 16 is we're going to say, hey, all 3 of these, we're going to find the inverse and then graph the original and its inverse, knowing that they are inverses of each other, and then prove or verify it by doing the dashed line y equals x so we can see how it reflects. So the instructions are exactly what I just described. So example 14 here, I'm going to find it by doing y equals 2x plus 8 like we did earlier, and then swapping or switching at y and x, and solving for y by subtracting 8 to start, and dividing everything by 2. And then I'm going to replace f of x with y, or excuse me, y with f inverse of x rather. And now I can graph the original and its inverse. So I'll do the original in green, and that's y equals mx plus b. That has a b, or a y-intercept of 8, and a slope of 2, which means it goes up to right 1 or down to left 1 with a slope of positive 2 over 1. So it's going uphill from left to right. And then x over 2 minus 4, that's a slope of 1 over 2, once again positive, so uphill from left to right, and a b of -4, so it goes down 4 to start. And I'll do the dashed line y equals x. And we can note that, yes, each of these points are an equal distance away from each other, and away from, more importantly, the line y equals x. On to number 15, the exact same process. So y equals 1/3 x minus 1. Switch x and y, and then solve for y. So add 1 to each side, and then multiply each side by 3, giving you 3x plus 1 equals y. And then rewriting this as f inverse of x equals 3x plus 3. Oop, I wrote 1 a moment ago, and then I fixed it in my green step. So I did the original in green here, or the inverse in green, so I guess I'll just continue doing the inverse in green on this problem, even though I did the inverse in light blue last time. And that slope is 3 over 1, so I'll go up 3 right 1, or down 3 left 1. Once again, it's positive, so it's going uphill from left to right. And then I'll do the original in purple, so I'll go down 1 to start, and up 1 right 3 with a slope of 1/3, or down 1 left 3. And I'll do the dashed line y equals x. And you can see, once again, that each of these are an equal distance from that dashed line and perfectly mirror each other across that dashed line. Last but not least, on to number 16, x squared minus 4 restricted to when x is greater than or equal to 0, so we're only graphing it in this portion of the graph. Y equals x squared minus 4, swap y and x, add 4, square root both sides, and we're also going to restrict this to only the positive versions of x and only the positive side of this axis, which is the reason we're doing that, to only be on this positive side. And so that'll be f inverse of x is the square root of x plus 4, acknowledging that x must be greater than or equal to negative 4. So once again, keep that non-negative. And so graphing this one in the purple, we haven't graphed square root functions here, so I'll just go through kind of a bit of a quick hit of it. So essentially, for x squared minus 4, the original, what I'll do is I'll just go left 4, and it would end up looking something like this. And for square root of x plus 4, oh, my apologies, I did that wrong. We've gone over graphing quadratics. I was flipping them wrong. I was doing the square root one first. For the original x squared minus 4, we've certainly done that. That would be going down 4, 1, 2, 3, 4, with the translation there. And it would look something like this. And then for the square root of x plus 4, we haven't done it, so I would go left 4. How that works. We do the opposite of this. This is a liar, just like it has been when it's ever with the x. And it would end up essentially just doing a lot of the same things and mirroring, which you might expect at this point with these dashed lines. I'll do the dashed line in blue this time, since the red won't really pop with the orange. I guess I shouldn't have done orange for the inverse, since I did orange for the original. There we go. So purple would be the inverse, and orange would be the original on this one, where orange is the quadratic like we normally do, even though I messed it up initially when I was graphing. And then purple, is the inverse, which is square root, which we haven't done, but it follows the same rule where the number with the x is a liar. And we would hit this point. I just accidentally missed it. So that wraps up our graphing portion, which wraps up our entire section of Section 7, which wraps up our unit of Unit 6 for Algebra 2.